Based on some of the feedback that you guys had on the Interactions 2.1 assignment, that it might be helpful to actually just do a couple examples that are directly off of Interactions 2.2, so that you've kind of got at least some concrete examples of exactly how we want you to approach these problems. So I thought I'd look at number one first, and then in a subsequent video I'll also look at another slightly more complicated problem. So let's look. We're going to look at the simple problem first. So the simple problem is basically we have this mass, right? It's suspended by two cables, right? Each of the cables is at some angle theta, right? And that angle theta is initially, pi over 4 or 45 degrees. And if I recall rightly from the description that's written, this is point A, this is point B, and this is point C, right? And so the first question that's asked is, what's the tension in the cables? So there are sort of two tensions you can think about here. Obviously, there's the tension in cable AB and the tension in cable BC. So what's my strategy going to be for solving this? Well, the first thing that I want to do is I want to actually just draw a free body diagram, right? That's the first step that I'll take. And that will actually force me to really think through a lot of what the forces are, where those forces are applied, or the extent to which I know where those forces are applied. The second thing I'm going to do is sort of translate that free body diagram to a sort of more formal mathematical statement of the requirements for the system to be static, or the system to be in equilibrium. So mathematical statement of equilibrium. Right? And in doing that, I'm actually going to bring to bear some of the sort of vector ideas that we talked about earlier, and also, of course, ideas about what the sort of nature of different sort of interaction models are. Okay, so finally, once I've translated that, I'll then use that mathematical statement in order to determine whatever I'm after. So in this case, I'll be using it to determine what TAB is and TBC are. Okay, so that's my strategy for solving this problem. Let's start with the free body diagram. So I've got a box that I've cut out of the universe. One interaction between this box and the rest of the universe is the gravitational interaction, right? All of the sort of particles that make up the Earth are pulling on all of the particles that make up the box. And so I abstract that distributed force to an equivalent force of gravity that's acting at the center of mass, right? There's my gravitational force acting down at the center of mass. The other way that this box is attached to the universe is via these two cables, right? And so at the top of the box, I have a tension that's in cable BC that's being applied, and also a tension that's in cable AB that's being applied, right? And I know what the directions of those are because the tension can only be applied along the string, right? A string can apply a force along the string, but not perpendicular to the string. But I don't know how big they are, right? So I've drawn my free body diagram at this point. Okay. Second thing I need to do is translate this into a statement of equilibrium. And my statement of equilibrium, you'll recall, is that first of all, the sum of forces on the object has to be 0. And secondly, that the sum of moments on the object is 0. Okay. Let's think first about the forces. It'll turn out in this case that the moments are trivial to think about. But let's think about the forces first. In order to write this out, I need to actually define a coordinate system for the problem. So let's think about at least the directions. Initially, we'll think about where we want to put the origin when we're dealing with moments. So there's I hat and J hat. J hat points up, I hat points to the right. Notice that these tensions are not pointing in the I hat or the J hat direction. And so what I'm going to do is actually define two unit vectors. I'm going to define the unit vector r hat BC that points from the connection point up to connection C, and also the unit vector r hat AB that points from the connection point up to point A, right? And I'm going to do that without referencing angles initially because I want to just develop a general expression, and then we'll deal with the angles in a second. Okay, so given those definitions, I can now go ahead and write the sum of forces, right? The sum of forces are going to be minus mg in the j hat direction, right? That's a gravitational force, plus TAB in the RAB hat direction, plus TBC in the R hat BC direction. And I probably ought to call this R hat BA instead of AB, but I forgot the notation I've got. Okay, and that has to be equal to 0 in order for my requirement that there be 0 net force on the object to be met. Okay. Well, if I'm going to solve this, I need to actually go a little further and figure out how do I express R hat AB and R hat BC. And so if I look at what that vector is, right, so here's what R hat AB looks like, right, it's got a unit length of 1, this angle is theta, if this angle is theta, so it's pretty clear that R hat AB I can think of as, or R hat BC, sorry, R hat BC is cos theta I hat plus sine theta j hat, right? And by the same token, I can make the same kind of analysis about R hat AB. R hat AB points in the negative x direction, but the positive y direction, it will turn out to be minus cos theta I hat plus sine theta j hat. Okay. So now I've got, now I can actually write this expression out a little bit more explicitly, right? So let's go ahead and do that. I've got minus mg j hat plus TAB times minus cos theta I hat plus sine theta j hat plus TBC times plus cos theta I hat plus sine theta j hat. And that whole vector quantity has to be equal to 0. Well, the only way that vector quantity can be equal to 0 is if each of the components are equal to 0. In other words, all the j hat stuff has to add up to 0, and all of the I hat stuff has to add up to 0. So let's write the I hat equation first. The I hat equation says that TAB times minus cos theta I hat plus TBC times cos theta I hat has to be equal to 0, right? In other words, and if we look at this, it's pretty clear that TAB must be equal to TBC on the assumption that these two angles, right, that these are both hanging down at theta. Right? Obviously, if they weren't both hanging down at theta, then you would have a different situation, but they are both hanging down at theta. Right? So we actually have eliminated one of the unknowns here. We know that these two tensions have to be the same. Okay? The second thing that we can do is say, okay, well now let's write the j hat equation. And our j hat equation says that minus mg j hat plus TAB times sine theta plus TBC times sine theta, but TBC times sine theta is actually TAB times sine theta as well, right? Because we just established these two were the same, are equal to 0, right? In other words, TAB must be equal to mg, right, divided by 2 times the sine of theta. Okay? So at this point, we've figured out what the tension is in the first cable, right? And that's the same as the tension in the second cable, right? And it's equal to the gravitational force divided by 2 times the sine of theta. Now let's think about that for a second. When theta goes to 0, right, what happens? Well, this thing blows up when theta goes to 0, right? So if I were actually trying to hold this up with the two cables being flat, I would need to have infinite tension in the cables to hold it up. On the other hand, if theta is pi over 2, right, then both cables are basically pulling up, and I get just mg over 2, because the sine of pi over 2 is 1. And so I've got half of the force of gravity being picked up by one cable, and half of the force of gravity being picked up by the second cable. So by doing it this way and sort of thinking about just in general sort of what's that RAB hat, what's that RBC hat, I'm able to get an expression that not only solves the problem for the 45-degree case that you're given, but actually also answers the second question, which is what happens as I pull these two connection points apart. as I increase the distance between the two connection points, the tension increases. And the reason the tension will increase is that angle is going to get shallower and shallower as you pull the two things apart. Okay? So I hope that gives you a sense of what the steps are in dealing with one of these statics problems. In the next video, we'll look at a little more complicated example.